Welcome back. So today we are going to look at a very interesting application of networks. We've already briefly looked at it when we looked at the game on wax a few classes ago. How does disease spread on networks and how can you capture that using networks? So networks are obviously very useful for modeling the spread of disease in a population. There are other kinds of models that people have used. You may have heard of the SIR model, where you have three types of people in a population. There are susceptible people, there are infected people, and there are recovering people, and so on. And there are various enhanced versions of this that people tried to use to capture the spread of COVID, because COVID was a very unique disease and very fast spreading disease, and the biggest challenge being there are lots of asymptomatic people, right? And this was the huge challenge that people had to contend with in the very beginning of the pandemic, wherein you didn't know that somebody was infectious, but well, they were spreading the disease without showing any symptoms. And this made it very challenging to obviously contain the disease and so on, but also to model and capture the growth and make projections, because it's very important for you to figure out how many hospital beds are required, or for you to project the oxygen demand that is there in the hospitals and so on. So these kinds of challenges require modeling using various kinds of methodologies, and you can imagine that a network based modeling makes a lot of sense, simply because in a classic SIR model, the assumption is that you have a well mixed population where you have some people who are susceptible, infectious and recovering, and they are all moving around. But when you have lockdowns, and when you have nationwide lockdowns or citywide lockdowns and so on, you know that people in one part of a city, certainly people in one part of the country are not going to interact with those in the other part of a country. But even within a local population, you have highly limited the flow of the virus or whatever is the causative agent for a disease or a pandemic. And the mathematical models of disease spreading typically use ODEs, and they assume a sort of homogeneous mixing of SI and R, as I was mentioning. And in fact, when you have those kinds of models, you can only make a case for mass vaccination or mass lockdown. But when you have a network level resolution, we did see the other day, right? So how do you find out the right people to vaccinate? Who do you quarantine? How do you disconnect a network so that you curtail the flow of the disease or the explosion of the pandemic? And if you have a very high resolution network level data on this, as we will see shortly, you can ask very interesting conditions. What time should you impose lockdowns, right? It may not work because depending upon when you impose it, it's going to push people to the other slots for interaction and so on. But still you can answer some interesting questions. In fact, night curfew was a very standard strategy that was adopted in several states across the country throughout the declining phases of the pandemic, right? Probably this helped the pandemic to a steeper decline. And who do you target for vaccination? Right? We obviously start off with health and frontline workers, which made a lot of sense. Common sense obviously, but also network sense, as we will see. And what are the key locations to impose lockdowns on and things like that. This is a paper that really predates the pandemic. So this was written in 2004 by Eubank and co-workers. They developed this very nice agent based simulation tool called EpiSims 3 to study disease outbreaks using social networks. They modeled the social contact network as a very nice bipartite graph again. So you have this bipartite graph of GPL, so where you have people and locations, right? So there are two types of vertices. These are the people, and these are the locations. So this tells you that person 1 was in location 1 from 8 AM to 12 noon. Right? So vertices in this graph are labeled with either the demographic or geographic information, and for example here we have arrival and departure times. And disease transmissions occur primarily between people who are co-located, and the spread really happens when the people start moving around. So they looked at two different projections to make a people network and a location network. Let's see what that is. But let us just quickly understand what this network is. So you have these dark circles which represent people. So there are 4 people who visited 4 locations. But if you see, is there an overlap, right? So you see that these 2 people overlapped between 9 AM and 10 AM at this location, right? And even though all three of these people visited this location, there is no place where these two people met each other, right? Except for that incident at 10 a.m. if you are really particular. But basically they did not overlap at all, because when this person left this location is when this person entered this location. So there is no way there could have been a disease that is spread between these two. But this person staying for a longer time in this location has interacted with this person and this person. So maybe this person could spread a disease to this person and this person could spread a disease to this person. So finally the network is all connected, right? Even though there was no direct interaction between this, so maybe with names it will become easier. Even though there was no direct interaction between B and D. Right, but B could have passed on the disease to C and C could have passed on the disease to D. Okay. So what is this projection? So we have a projection of GPL to GP. Okay. So you know very well how to make these projections. We just saw a few classes ago how there are disease genes that we saw the disease home where we split out the disease genes on the one hand and the diseases themselves on the other hand. So here is your GP and you can resolve it on a time based notion as you can resolve these interactions on a time basis as well. So at 8 to 9 a.m. this is how the network looks like. So these two people are interacting in location 1, let us say A and B, or let us just call them P1, P2 might be better, P1, P2, P3, P4, L1, L2, L3, L4. So P1 and P2 overlap at L1 from 8 to 9. Between 9 and 10, what are the overlaps? You have P2 and P3 overlapping at L3. From 10 to 11, you have P3 and P4 overlapping in L3 again. Right. And 11 to 12, you have no overlaps. P1 is in L1, P2 is in L2, P3 is in L3 and P4 is in L4. So there is no connection if you are looking at the 11 to 12 time frame, right. You can also make a GPL to GL projection, wherein again you have, let us label them, have P1, P2, P3, P4, L1, L2, L3, L4, and what you have is at 9 o'clock there are people from location 1 who go to location 3. So these two are connected, whereas at 10 o'clock you have people from, you have both people from location 4 going to location 3 and people from location 3 going to location, interacting in location 2. And at 11 o'clock you have people from L3 and L4 being connected. But if you combine these, right, and make a static projection, removing this time resolution, you will see that there are far more interactions, right. So P1 has interacted with P2, who has interacted with P3, who has interacted with P4. So you could have well passed a disease from P1 to P4 in this between 8 and 11 itself. So this is the projection that they called GP hat, where you basically remove the time resolution to make a simplified graph. You can do the same thing for here as well. So you had some people going from L1 to L3 and then L3 to L2 and L3 to L4 in different times, but then you can remove the time resolution and come up with a location graph. This is directed because it shows you the direction in which people flowed from one place to another, and what you now have are two different graphs. You have GP and GL. So GP hat and GL hat, and these two networks are not time varying, but they sort of represent the synthesis across time scales, across time points, and what you have is a sort of upper bound on the interactions, right. So you know that P1 never came into direct contact with P4, but P1 can still pass the disease from to P4 via P2 and P3. So these are the kind of things that this graph can capture, and then you can perform a lot of simulations on this. So this EpiSims 3 was the tool that they developed, which is able to capture many of these behaviors. So what is the data source for building something like that? It's quite challenging, but today you have lots of Google mobility data and things like that which you can readily rely on. There's also Facebook data. There are lots of people who willingly or unwittingly share their location data and so on, and well, at an anonymous level this is highly useful, especially during scenarios such as a pandemic, and land use data, traffic data and so on, and of course GPS data and things like that. And very many applications arise because you are able to build these kinds of complex networks from a huge number of data sources. What are the applications? What are the maximum people at risk for a disease originating from a single infected person, right? So this could be captured by the single largest connected component in GP. And what are the key locations to impose lockdown? So this could be captured by the node with highest centrality in GL hat. What is the time of lockdown? So you look at the time graph with the most number of edges in GP and so on. What are the key locations to impose lockdown at a given time? You can look at the nodes with highest centrality in GL at a given time point. Who are the most important people to be vaccinated? Look at nodes with the highest centrality in GP hat and so on, right. So where do you place sensors, how do you trace contacts and so on and so forth. So you see that this kind of a framework, this shows you what is the quality of a model, the utility of a model, the versatility of this kind of a model in capturing various aspects of a disease spread in a pandemic situation, which unfortunately we've all now become all too familiar with. This brings us to the end of another interesting application of networks, and you see that the applications of networks actually spans a very broad spectrum, right. We started off with certain applications where we looked at molecular graphs, we now looked at differential network analysis, we've looked at disease gene networks, and now we also have looked at disease spread. We also looked at disease modules in different kinds of networks and so on. So there are a huge number of applications for network biology in a wide ranging set of scenarios.